make sure that you filled out the form which you had in the registration folder with the original receipts. And if you do have already a receipts that you can leave with us, especially if those of you who are flying, then it'd be very or even if you have electronic train tickets, that would be good enough. Just please do this immediately, so that would speed up the whole process. Is there anything I should say? Anything more I should say? Eleonora, anything more I should say about this? Okay, so yeah, thanks very much, Eleonora, for everything. And I'd like to thank as well the Andrea Freccioni, who's not here at the moment, who's been recording all the sessions, and everyone else who's been helping out with letting the whole thing run smoothly. So again, thanks very much, everyone. And that brings us to the final act of this 3 days workshop. And it's just my big pleasure to introduce Silvio Micali, who'll speak about Knightian Analysis of the VCG. Thanks very much.
Good afternoon, ladies and gentlemen. Let me start with my own thanks. Thank you, first of all, to Pierpaolo and the organizer for inviting me, much appreciated. Thank you all for the splendid lectures, and finally, thank for the festive and interdisciplinary atmosphere that makes this workshop very special. So let me start by paraphrasing our national poet. In the middle of this life of mine, I fell in love with mechanism design. And I must say, because traditionally I'm not a game theorist at all, or nor a mechanism designer, I'm coming from outer space, maybe not so alien, but alien enough. And by being, somehow a foreigner in a new land, comes with some advantages. And the advantages today is that I can feel free to go on a limb and talk about something a bit more esoteric that otherwise I would have in my own field. So, mechanism design, so what is it? I'd like to define it like optimization without information. By the way, if you want to choose an optimal outcome and you have the data, you know that computationally it can be extremely hard to find the optimum. But if you don't have the data, it cannot be any easier. In fact, it can be much harder. So where is the data? So I'm a decision maker. I want to make my people happy. I want to choose an optimal outcome for them, but unfortunately I don't know what they like, so how can I do that? All the information is with rational players. Now, we've been talking about what rationality can be. Irene, here, rationality is very simple, greed. These guys want to make money, so they want to maximize utility, okay? Nothing else matters, okay? But they can be very clever in finding out to maximize their utility. So, we want to leverage the rationality, so defined of the players, so that they reveal enough about what they want, so that we can choose a good enough outcome. So that's what it is, we want to engineer a game. So game theory, typically the game is given and you analyze it. Here we want to engineer a game so that when it's played by rational players, we get the outcomes that we want. Now, that sounds very difficult, so let me give you an example. In the simplest possible example that I can give, and in fact, an example that was discovered at least 200 years ago. And so we have a very big goal. We have a beautiful painting, and the proud owner of this painting, unfortunately, is on his deathbed, and is going to part with this work of art. And so he wants to give it to the players, to the one who loves it the most, so that they can enjoy it as much as he enjoyed it. And to do so, he's ready to do anything, even to use money to discover who loves the most. What's the use for money if you're going to heaven? Nothing. So the money then he can give it to charity, okay? But he really wants to make use of money and anything else he can, so that he ensures that the painting goes to the player who values the most. The players there, these are rational people. They know in their head what their value for the painting is. Problem is that if the guy here knew who loves the most, what's the difficulty? If you want to maximize the social welfare, which means you want to make the people as happy as you can, you give it to the one who values the most, the blue player. Unfortunately, he does not have this information. So perhaps he can have actually maybe a Bayesian distribution. Says, not at all. This guy is really as ignorant as you can be. That's the setting where we are. There is a decision maker, ignorant as a goat, and he wants to fulfill his dream to give the painting to the player who values the most. By the way, it is indeed a beautiful image. If you are interested in acquiring it, just let me know. So, here is the single good mechanism. Now we want to engineer a game, and it's going to be an auction game, as a particular name, that ensures that the painter goes to the thing. So, how does an auction go? Players bid. What are bids? Integers, without a loss of generality, right? So you bid something, and then the mechanism should decide, process all these bids, and spits out outputs, to be more polite, an allocation, so the player who wins, and the prices, how much everybody ought to pay. In general, you charge the winner, but in general, you can have a price of entry, right? So that is... Okay. So what about the obvious? So if you ask me 5 years ago, what auction I would design this to satisfy this problem. I would say, well, you guys bid, and here let me tell you what I'm going to do. How am I going to process your bids? I choose the highest bidder, and I give him the painting, and I cash out whatever he offered. Right? So if you bid 100, you get the painting, and you give me $100. Now the problem is that this mechanism does not satisfy the maximization of social welfare, and here is why. Assume that I'm rational. Well, rational means it's greedy. What I want to do is maximize my utility. And assume that I really value the painting 100. Should I bid 100? No. Why? Because if I don't win, it doesn't matter. The status quo prevails. I pay nothing, I get no painting. But if I win and I value the painting 100 and I give you $100, which by definition I value 100, is a wash. Right? So what is my utility? It's zero. In fact, why should I put on a jacket, a tie, and go show up at the auction? Because even if I win, it is a wash. So I might as well leave the jacket at home and proceed with my day. Maybe I go to a coffee shop, enjoy a cappuccino, and have something better to do than to have zero utility. All right. So here, in fact, is a better idea. And the better idea is called the second price mechanism. And is very, very simple, but also very, very ingenious. In fact, it's the archetypal mechanism. It proceeds as follows. You bid a number like before. The highest bidder wins, but he or she pays not to what he or she bids, but the second highest bid. Okay? Says, okay, it's a little bit weird. What's the advantage now? The advantage now that truthfulness becomes a dominant strategy. Okay? So what does it mean, dominant strategy? That is in your self-interest to tell truth, to bid your true value for the painting, no matter what your opponents might do. How do we prove this? By a case analysis. Many cases, we analyze together one to give you just the zest of it. Okay, assume that I value here 100, and actually the highest value. And the second bid is 80, like in the minds of these players, right? And I tell myself, I understand the rules. The highest wins pays the second highest price. I say, well, should I bid even higher? Well, in this case, it wouldn't matter, right? Because if I bid even higher, if I win it like this, I would win still now. But what do I pay? I still pay 80. So I have no incentives to bid higher. Well, do I incentives to bid lower? Assume I bid 90. Well, I still win, but do I pay less? No, because I still pay the second highest bid. If I bid even lower, well, whoever bid 80 now wins, and I lose the possibility of making a spread of 20, right? Case 1 out of n. I don't know how many cases there are, but it's all very similar elementary logic, very, very powerful. So when somebody is clever enough to design this mechanism, the players are rational because in the sense that they understand to maximize things, they actually do mathematical reasoning. They realize that being truthful is the best thing. So what do you expect? That they bid truthfully. And therefore, when you execute the mechanism, by magic, you choose, even though you did not know beforehand, the blue player, you give the painting to the right play, you get the $80 that you didn't care, you give the Knights of Santo Stefano, and you proceed. All right. What's not to love about it? That's why I fell in love with this thing. And however, love is a very tricky thing, because when we really love someone, you want to transform him or her into something else. And that's a problem, right? So I'm trying to love, as a sign of love to mechanism design, I'm going to make now some strange twist about it. Here is the limb I want to go to. And the limb is the following. I want to address the following question. How much can we decrease our classical assumption and still be able to design mechanisms that perform reasonably? By the way, if you are an economist, you realize that goes against 99% of the field, because in the field is, I want to have a certain goal for sure, and the question is, I'm going to make as many assumptions I need to achieve exactly this goal. I'm going to go the other way around. I want to assume very little, and I want to see how much can I get, reasonable can I get. All right. So here is agenda. I'm going to tell you one model. We can survive that. Then we can give you some theorems. Nobody at the end of a conference in the middle of the afternoon can survive plural some theorems. So not to worry, I'm going just to explain the theorems, and we can discuss afterwards some proofs, and then finish up with some personal hopes. Good. So let me tell you about the model. So what is the classical assumption? The classical assumption, you go to an auction, is that a player I here, is defined by his own payoff type. In the case, which is whatever information defines him in the strategic interaction at hand. In this particular strategic interaction, what defines a player? It doesn't matter if he's blonde or brunette or whatever. What matters is that how much he values the painting. The valuation of the painting. That is the quintessential at the heart of this player. So, but that is not an assumption. That's a fact, or if anything, is a definition. What is the assumption? The assumption is, and that is a classical assumption, that each player knows his own type exactly. Theta I star exactly. So that means that his own type is not just embedded in you in your DNA. It's actually a bit more available to you. You are aware of it, as we discussed before. It's in your head. Now, something in your heart I don't mind. In my genetic code I don't mind. But there are things in my genetic code that are not in my head. And speaking of philosophy, Socrates admonishes us that it's very hard to know yourself. He didn't quite say that, but if I remember correctly, he said, know yourself. But he told us so. Why? Because it's hard to know yourself. So, what we wanted is to allow for self-uncertainty. Can we somehow have a mechanism design when the players do not know themselves very much? All right, say when I talk about uncertainty, after 200 years of a triumph of probabilism means, you mean that the player knows a distribution, right, from which his own true price is. You must know at least that. Strikes me as an exorbitant amount of knowledge and information. Because if you think about it, for any possible value, how much do I value this lamp here? I have a distribution. Can I love it $13,273? Maybe. Or $1,275. If I know the distribution, I'm actually be able to tell you precisely the exact ratio between any pair of the probability of a possible valuation. And I do not have such an accurate knowledge about myself. Proof. If you see the program, talk by Silvio Micali to be announced. I didn't know how to until hours ago what I'm going to do. I did the slide even during lunch. All right. So, are there weaker models? Okay, here is our model. Well, you ought to know something, right? But what you know is a set of valuation with a guarantee that one of the elements in the set is your valuation. You see, hidden there in position, I think, 2 is theta I star, but I have no idea. So let me give you this example. Assume here there is one player, he values anything between 2 and 5, that is a compact real interval, or is the union anything between 2 and 5 or between 7 and 10, but for some reason not in between. Or this guy is very discrete. My value is either 3 or 11 or 17, the end. Okay? Very tough player. And so first of all, you should say, well, this is not convex. How can it be? Well, I mean, it can be, I can justify, but I have to talk more about the model than I want to, so I don't justify it for now. But in any case, think about me, I really can go between A and B and not A plus B over 2 easily. Right? But we can talk about this too. To have a full general thing, I want to put myself at the edge of a precipice. I don't want to assume that things are, why should they be convex? I have a very sharp knowledge, very sharp edges, very, very discrete if needed. That is a kind of even in the worst case, a mechanism should be able to do something. All right, let me tell you that this model actually is very expressive. I know what to say. Listen, how can you have 2 alternatives, even A or B, and not be able to form at least some subjective beliefs about them? Say, maybe you feel that B is more probable than A. You don't know the probability, but at least it's more likely, right, in some generic sense. No problem. So let me give you an example. Assume that exactly a player like this. I know that I value 10 or 20, but I think it is more probably 20 than 10. I can re-express this by saying this. Look, I have a distribution. I look at all the distribution that give weight only, whose support is only 10 or 12, and I'm saying the possibility, the distribution that I'm envisaging for myself are the ones that give more probability to 20 than 10. Okay? So for instance, they could be 50-50. In such a case, the average would be, if I am a risk-neutral player, if I know that my evaluation is 10 or 50-50, 20 or 10, I can think and play the auction as if my evaluation is 15. But because I said that the distributions is more likely, strictly most likely, so essentially, if you take this infinitely many distribution, and then you are risk neutral, and therefore you take the expectation of all distribution, is something to express that is 10 or 20, but more likely 20, corresponds to I am a player who thinks that my set is the set of numbers, the open interval on the left, closed on the right, between 15, 15.21, 0.2, up to 20, all of them. So, when I say that a set of candidate set, a set of evaluation candidate set for me is Ki, if I'm player I mean that all my beliefs have already been taken into account, okay? There is nothing else. When I'm left, I really have a set. I have a set theoretic uncertainty about myself. Is this clear? Why do I want to study this model? Motivation, motivation, motivation. Well, let me start with the practical. So first of all, when you are undecided, a new technology comes up, and you say you want to acquire your firm, should I buy this, invest in G5, next G6, G17? Says they want a ton of money for generation 17. So what do? You call experts. Gandalf, Dumbledore, Potter. I would love to be an expert. If you want to hire me for an expert, I will give you an expertise. I will give you an answer, for sure. And these guys will too, but they will disagree. Now, tradition will say, what do you mean? An expert is an expert. He's going to tell you what the value of G17 is to your firm. Well, I beg to differ. Different expert, very often can give you a different answer. And even if you believe that one of them is giving you the right answer, go and figure out why. Let me give you another example. Do you know what this is? Bitcoin. The young generation recognize it at a glance. Trivial question for the young. So that's a Bitcoin. Now, what is the value of a Bitcoin? Let me tell you that it certainly fluctuates, okay? But let me tell you something that is not clear to everybody. People want to buy this Bitcoin. But Bitcoin, I'm going to say, is very difficult to evaluate how much it's worth. Why? Because you have to take in consideration, is going to remain legal, say, for the next 25 years? Or, what is the likelihood that other cryptocurrencies will arise in between now and 25 years, etc., etc., etc. But then, Bitcoin is a value, if and only if a mathematical assumption that nobody has been able to prove so far, as remaining unproven for 100 years, is that there is such a thing like a collision intractable hash function, H. Why? Because if these guys don't exist, I can make a Bitcoin when I'm giving the talk, and so do you, and Bitcoins are for free. So I claim that if you believe, if you are, there are those guys that they believe as an axiom, that if you don't know something, and you are a human, you cannot but make a distribution. You are forced. I believe that I'm human, and I refuse to take that path. But because what is the probability of a mathematical conjecture to be true? What does it mean? So let's be concrete. What is the probability that Riemann's conjecture is true? 33.5%? What does it mean? You cannot put, not everything you can attach a probability. So even if you are really believe that everything you should model as a distribution, you are forced, I claim, but most people will disagree, that in a Bitcoin you should end up with two probabilities. One, in which you computed all the legality, the cryptocurrency, the rights, one probability. And the mathematical assumption is true. And the other one is mathematical assumption is correct, and I can tell you the value is 0. So at least you must have the two possible things. All right, is enough motivation for the practical. Let's go for the theoretical. Uncertainty has been modeled by probability distribution very successfully for 200 years. Don't you think it's enough? I mean, there has been a monopoly, and if it were not for the heroic efforts of a few of us, it would have been a tyranny. There is nothing. So I really value the possibility to explore set theoretical uncertainty. And really my purpose here is to say, is this set theoretical uncertainty leverageable to get a good mechanism out of it in mechanism design? And finally, let me tell you the personal thing. Look, this stuff is challenging and fun, and we need fun. I mean, this as a motivation is a little bit ivory towerish, but the moment in which we stop appreciating beauty, the world is not worth living in it. So that seems to me is a good enough motivation. So I guarantee you that to do this type of analysis is actually fun and obliges you to develop a new set of techniques, and you'll love it too. Okay, enough motivation. I feel motivated. Where do I start? Well, I suggest to start at the second price mechanism. Why? Because it's the first mechanism. It's the quintessential mechanism. It's the mechanism that we know everything about it. If you have to start something new, you might as well start on the field, on the turf that you know best. So that seems to be a good choice. Very good. By the way, don't read it because there are symbols here. What I mean, all the definition of what is an allocation remains. Whether the player, an allocation is who gets the good. The price is how much pie you pay, right? So the social welfare is really the sum of the valuation, never mind what it is. But I'm saying the only thing that changes is that players no longer have a single valuation, but each player has a set of valuation. So the true valuation profile is an element of this cross. My utility depends on something that I don't know. Depends on what valuation in my set is really my true one. For instance, I may participate to an auction and realize 2 years later that I had no use for what I bought at the very beginning, because my TI star was 0, if 0 was 100. And the maximum social welfare is still defined implicitly over the true valuation, okay? The players don't know. The designer does not know, but these things are defined implicitly through this hidden true valuation that we do have. Okay? Yep.
What is your motivation for the truth axiom that theta belongs to K?
Because I'm a simple man, and at the very end, I really believe, that, as we said at least in 2 occasions today, that one occasion, I think it was Enzo, to say, we take it for granted the world has to be true, or something about the world. So there is a reality. I want to go on a limb, but not too far on that limb before the thing cracks. So I think it is possible to develop a a fear of all pure subjectivism things. But I'm not today. I decided to start by embedding that at least, even though my knowledge has an element of truth to it, in the sense that is set theoretic, but one of them is really the truth. You are right. Next step would to be, well, how about we remove that too and see what happens, right? But not today. All right. So by the way, so when you have an outcome, outcomes can be incomparable. Never mind. What is an outcome? An outcome is whether you win or not, who gets the goods and how much you pay. So assume that outcome 1, you win the good and you pay 25,000. Or you don't get the goods and you paid 0. Which one you prefer? Well, it may be that it varies, right? Because if one of your TI in your candidate set, your valuation is 10,000, you're losing money and you're better off in the other way. If instead in your candidate set there is 100,000 and that has your truth, you should prefer it. So it's very hard to compare. So we are in what the game theorists would call in a Bewley incomplete preferences. Okay? Good. By the way, incomplete preferences have for sure addressed. In fact, we are talking about ambiguity for 3 days. I suspect also the first day, right? And so indecision theory is certainly starting with Aumann and others as have been. And in particular, I want to say that, look at the last 3. These are various mechanisms to say, well, if you don't really know what you have incomplete preferences, which button you press, and it really depends. Somebody says the max, you are optimistic. The mean, you are pessimistic. The average, right? Let's showcase expectation that I don't even know what it is, but I put it there because they told me to. So there are various strategies to say, to force a player who has set theoretical uncertainty to actually declare something. Why? Because we refrain from this uncertainty, too much uncertainty. I want to carry this uncertainty till the end. I don't want to complete preferences. Inequilibrium models have been considered, and actually also in mechanism. There is a paper by Lopomo, Rigotti, and Shannon for a single-player mechanism, but still a mechanism. But it's a little bit, it's called for a variant extraction. And it is a model in which the player has his own true type in the heart, but also has true type in the mind. It's where does ambiguity rises? Ambiguity rises that there is a state of the world, S, which the mechanism knows, but the player does not know, but it affects what his utility is. The only thing that the player knows is a distribution about S. So you see, it's a different type of model in which the mechanism really knows it all. Here I want to work instead in a totally ignorant decision maker. Good. You got the model. Model is only good if we can accompany them with some theorems, right? The theorems is the sugar that allows you to take the medicine of the model. A model without theorems like medicine in the sugar. Bad idea. Okay. Okay, but what type of structure, what type of theorems are we looking at for? Well, I want to analyze social welfare. I mean, I want to allocate the good so as to maximize the happiness of the people in single good auctions. But so, what do I need? I need a performance measure, which tells you how good is, how much I can approximate somehow the best possible outcome. And a solution concept, how will the player reasons facing the mechanism given their own uncertainty about themselves. Let's start with the performance measure. Assume that we have here a red player, and these 5 red dots, this player is very discrete, my evaluation is either that dot, or that dot, or that number, or that number. So I want to look at the spread between the highest value and the smallest value, and I call it delta I. I want to say that is a measure of the uncertainty of the first player. And then I want to take, well, that is your uncertainty will take the maximum, and that is the uncertainty of the setting I have in my hand, is delta uncertain. Okay. And let me tell you that it says, okay, that is not a measure of performance, that is a measure of uncertainty. So let me click here, and let's go on performance. The performance of a mechanism will depend on how many players there are. You know what? If there is, of course it depends, because if there is one player, even if voice is uncertain, and you are the only player, you want the good, I take the lamp and I give you, I'm done. I maximize social welfare because he's the only guy around. So you ought to depend on that. You also to depend on the rational choice of strategies of the players. It also will depend on where the true valuation lies in the sets, but it also depends on the set themselves. In particular, it has to depend on the inaccuracy delta of the set. And let me give you intuition. The inaccuracy can go from 0, 1, goes very far, and the guaranteed social welfare, it could be the maximum or 0. And so here comes the players, and assume that the inaccuracy is 0. So everybody knows the valuation perfectly, is a single number. Then the second price, as I proved to you with the 2 fingers proof, guarantees that the good is well allocated in the best possible way. But it is intuitively clear that if these guys have a little bit uncertainty, well, I cannot be sure to allocate the good, right? Very well. And the more uncertain they are, the worse it gets, possibly, the performance. So if you want, the performance essentially is the social welfare that I want to go after. How well I will perform is a function of delta, of this uncertainty. If it's 0, I already know what to do. But now the question is do I do the maximum minus delta square, minus delta cube, minus something? It has to be a function of delta. That's how I want to evaluate the performance of mechanism. How about solution concept? Well, the first solution concept would be, as we know, dominant strategy, like in the second price, right? Which means, if you remember, a strategy dominant is my best strategy for me no matter what you do. But here I have another element, the red element of uncertainty. So my dominant strategy means if it is the best strategy for me, no matter what you do, and no matter what my true valuation is in my set.
Why is it maximum? What's the justification for the maximum there? It's not to represent very much the population. It's sensitive to wild people.
Right, because that comes from my tradition in which, I look very much in the worst case and I try to do the worst case to be benign. And I will succeed in this case. But I could actually do another thing. It could be the maximum uncertainty, the uncertainty of the player who's true. I could do something more implicit, right, depending on the truth. But to start, this much will work. I remember when I was a student and I saw the least square method, right, to interpolate points. And I was really upset because so far everything makes sense. And suddenly you say you want to find the curve that, a parabola that best fits all these points. And he says, but you maximize the sum of the square of the distance from the parabola. And he says, why the square? Why don't we do just the absolute distance, right? And remember, the professor told me 2 things. A, because the square we could do and this you cannot do. And 2, it doesn't matter which measure you really use. Any good measure, provided they can prove something, at the end it works, okay? So that is actually a good example, but we can, by all means, investigate others. All right. So but before we continue, however, I want to say, so it's clear what it means dominant strategy. But I want to say, no, okay, that's a definition. How can you work with a definition? How can you have a dominant strategy if you're self-uncertain? So if you know that your valuation is 10 or 20, do you really say that bidding 10 is the best thing you could do? Or bidding 20? Or even bidding 7, which is neither 10 or 13? How can you justify? How do you know? Well, yes, because in principle, because now that there is a new setting, we can enlarge the set of strategies. And it's actually very natural in this setting to allow the players to bid not a number, but a set of number. Because after all, you have a set of numbers that your evaluation can be from, so bid the set. In principle, there can be a dominant strategy mechanism that everybody bids his own set, and you make sure that his bidding truthfully is the best thing for everybody, and then it makes a reasonable allocation after that, right? It could very well be. My first theorem is that this is actually impossible. In fact, it is a bad idea to seek for dominant strategy mechanism in this setting. is a terrible idea. And I'm going to say scary like this. For all dominant strategy mechanism M, for all delta inaccurate profile or candidate sets K, for all i's, just a second, let's pass by one. Okay. For all, M is a dominant strategy mechanism, because you want a dominant strategy mechanism, you got it. M is dominant strategy, the generic, whatever arbitrary quantified dominant strategy mechanism. Now, let's say a delta inaccurate set, because it has to be delta inaccurate. So here are the set of the players. They're very simple, as interval, right? Let's say this is delta. I want to say, yes, that fits. Yeah, that is one delta candidate sets for everybody. Very good. For all I, which means there are a bunch of players, choose one. I choose that one. Okay? Good. So now I want to say here is, look at the probability that the mechanism allocates the good to the blue player now that we have identified when everybody beats these three sets. There ought to be this probability. It can be 0, it can be 1, it can be something. In fact, here it is. If it is deterministic, it's not even a probability, but in general, say, well, it's something in between 0 and 1, ought to be a probability, there it is. What does the theorem say? You start with this very generic thing, right? You bid whatever you want, you choose a player, you look at the probability that he gets under those particular set of bids, the good, and then you say that this probability stays the same no matter what the player one would have bid, provided it is delta inaccurate. In other words, look at this probability here. If the player I would have bidded this, which is still delta accurate, the probability will stay the same. If you would have bid this, it would stay the same. If you put this, it would stay the same. If you put that, it would stay the same. So, ladies and gentlemen, that is a proof as much as you can go without doing further analysis, that means that this dominant strategy mechanism is useless, and all of them are useless. Because at the end of the day, if these are the players, by definition, one of them ought to lose, because if there are even 3 players or one of them ought to lose. And so, if he loses here, he should have lost also if you bid all the way around. So essentially, it's totally orthogonal. Being dominant strategy and trying to maximize social welfare in the setting are really orthogonal, right? They are not correlated. All right. Wow. We no longer have dominant strategy. The king is dead. The first thing we should... Is this good or bad not to have dominant strategy? I think it's not good, not bad. It's a fact, okay? In this setting, dominant strategy don't make any sense. I mean, you can define them, but you don't get any performance out of them. But the king is dead, long live the king, seeking a new king. So here is my new candidate, the Dauphin, and his implementation in Knightian undominated strategies. What does this mean? First of all, let me tell you, what does it mean for a strategy to be dominating this strategy? Forget the picture, look at me. This strategy dominates this. What should happen? Is this better than this for me? Well, depends what your strategy use. Okay, fix your strategy. If no matter what strategy you use, this gives me higher utility than this, and no matter what my true valuation is in my candidate set, that gives me better than this, but it would be equal. Yes, but at least in one case of what you do, and in one case of what I have in my mind, this is strictly better. Should I ever use this? No, be irrational for me to do this. So, delete. Whatever you are left over is undominated. Makes sense, right? So if you have a best strategy, and you are a rational player, you play a best strategy. But if you don't have a best strategy, you never play a dominant strategy. So you are left with a bunch of undominated strategies, and what is my assumption that I'm making? Nothing but that you will use one of them. That's all. Okay? So it's not an equilibrium notion. And by the way, proudly so, I really don't believe in equilibrium. I think that Nash equilibrium is an historical accident, and people will ponder 100 years from now why the hell we paid so much attention to it. So this is not an equilibrium notion, okay?
So anyway, you're using weak dominance.
Yes. Okay, what is the theorem 2? That if you assume that even though I am uncertain about myself, I will never use a dominant strategy. Guess what? The second price mechanism, which does not ask you to bid sets or strange things, just one number, does very well. Define very well. This. Well, it isn't clear to me what it means, so I'll give you a picture, okay? So assume that you are a red player and these are your bids. Does it make sense for you to bid below your lowest possible valuation in your candidate sets? No. Why? Because if one of your, right, if one of your opponents, yes, bids here, the maximum of your opponent's bids here, then to bid this would have been a bid and bid this, because you would have won bidding this and pay this price, and you would get positivity whether your true valuation is this or this or this or this or that, right? That's pretty good. Should you bid above your highest possible valuation? No, same reasoning, right? So, that means that the set of undominated strategies is just the closed interval, not only the 5, but anything in between 2. You cannot disregard. You call this a theorem? It's so simple, the proof is already done. In fact, that's why I put quotes. But you see, this simplicity justifies why it was a very good idea to start with the second price mechanism. Because at least we have this characterization on the undominated strategies of these very well uncertain players. You know that nobody will ever exit this box. In fact, let's give it a name. It is a naturally bounded property. You don't exit the box of your uncertainty, of your KI. What is, in some sense, look, in this simple example, we can live, we may meet a Bueling complete preference and survive. Nothing has happened. And without any preference complete, so tell me what you are going to be max min rational or not. We don't need to. In the social well performance, by the way, you can guarantee the maximum social welfare minus 2 delta. Why minus 2 delta? Because assume there are just 2 players, right? That's a single example. So one player, his interval is this. And all of them are undominated for him. But he feels, and the truth is here. He's actually, the highest valuation is the true one. But he's pessimistic and he bids this. Then there is a second player. His true valuation is here, but he's very optimistic and he bids this, just a tiny bit higher. So this guy wins, and the social welfare you realize is this, and our answer is this. This is delta at most, that's why it comes useful at most. This is delta at most, so you're losing 2 delta. So I claim that that's pretty good. Why? If you don't like this type of analysis, you can start saying, oh, it's very good, only if delta is small. But come on, if you believe that people know themselves exactly, and then you say, okay, let's allow for the possibility that they have set uncertainty. Should delta be big or small? Well, until yesterday you said that you know things exactly, delta should be small, it should be plus or minus $100, it cannot be plus or minus $1 trillion. So that means that we can actually do damn good. But nonetheless, we are rational researchers too. What does it mean? That we are greedy. So I want to say, can we do better? But before this, I got ahead of myself and say, look, this is a worst-case benchmark. That's a bad form to use worst-case benchmark. That's what computer scientists use. But if you think of them as a worst-case guarantee, maybe perhaps is more palatable. Because it means that if you know that your player is uncertain and you use the second price mechanism, no matter what happens, you miss by 2 delta the best possible allocation. That is good to know. Because otherwise you may choose another mechanism and good luck to you. Can we do better? Somehow the second price, why did we choose it? Because it's the oldest mechanism. Maybe there is another one that somehow incentivizes people who have this interval uncertainty to bid a bit more in the middle of the interval, and so somehow perhaps we can do MSW minus delta. We can do better. Why not? The third theorem I want to say is that that is not possible, at least if you consider finite mechanism. So no finite mechanism can, in undominated strategy, guarantee social welfare greater than the best minus 2 delta. What does no mean? Mean any mechanism, not second price-ish, not classical, even think you could bid sets of valuation, rabbits, whatever you want, is not going to help you. But the set of strategy is finite. By the way, as a computer scientist, I think the world is finite. There are only 2 to the 300 elementary particles in the world. I believe that the continuum is a beautiful intellectual construct to maximize functions, to do other things, but not to represent the reality. But that is my personal opinion. So which means that assume that, look at mechanism in which you have to bid, say, a single valuation, but in cents, and you cannot bid more than 1 trillion. Okay, that's 1 billion actually. Right? That is reasonable, I'm saying. So no finite mechanism can beat this. And noticing this for the ones into the know that we need to have a universal quantifier, and this usually is very hard to beat. Something is not possible. For any mechanism you can think, tomorrow, to later, 100 years from now, that is very hard, right? When you have a revelation principle available, you have essentially to analyze the truthful mechanism. So you analyze 1, and you decrease this infinity to 1. Here, instead, we don't have in undominated strategy the equivalent of the revelation principle. So therefore, we must really defeat a quantifier for all. And it's not a simple thing. But what is the idea? It's doable anyway. And the idea to figure out a structural relation between, in any mechanism, no matter what the mechanism is, between the undominated strategy of a player in the mechanism and his candidate valuation set Ki. And let me tell you, by lying first, which is the easiest shortcut to the truth, what is the structural relationship? Means, take 2 candidate sets, Ki and Ki equals 1, that have an element in common, actually 2, at least 2. Then, their set of undominated strategy must also overlap. Okay? Remember, if the mechanism is arbitrary, I give you say, this is your set of undominated strategy is somewhere there. If your set was slightly different, in principle, they could go somewhere else. By lying, I'm saying they cannot. There must be something in common anyway. So let me tell you graphically, that is a blue candidate set for the player, and these are all the pure strategy given to player I by the mechanism. And that is a zoo. It is a zoo because now remember, without the revelation principle, the strategy could be anything. It can be penguin, lions, cats, anything. So the undominated strategy for this particular mechanism, once you look at the mechanism and give them a set of strategy, you identify these. And say, let's assume now that your candidate sets were slightly different. But notice, those will be the other set of undominated strategy. But notice that these 2 sets have 2 elements in common. And that is enough to guarantee that there is an element in common. In which case, the worth dog. Okay? Okay. In truth, what happens is that you may not have an element in common, but you have one element and one element that essentially utility equivalent. Close enough. And that is all we need. So, never mind the ugly truth, the lies thing. Okay, what I'd like to do, any talk should have a moment of incomprehension. And I'd like to open that moment, right? Mid-thing. Bad news is hard to understand, but actually not hard, but what is hard just because of the time of the hour and the end of the workshop make it hard. But I'm not going to prove the dominated intersection lemma. But I want to do the easy direction to prove why, if this were true in his false instantiation, then the social welfare, not deterministic mechanism can guarantee this, a social welfare better than 2 delta. And the proof is not bad. Proof. Take any mechanism M. What are the sets? Say, take an X arbitrarily, and this is a delta uncertain set of players, right? You start at X, and you go X minus delta, all of them. Okay? Consider the set. Okay, consider now, next. Consider another one just below, but not too much. Right? Each one of them intersects at least 2. Okay, consider, so what? Well, now I invoke the lemma. if these guys, they undominated intersectional lemma guarantees that there is an undominated strategy in common. Let it be S1, blue S1 for the first player, blue S2 for the second player, blue S3 for the second player. Okay? Now I want to say, if the player play these guys, hey, there is one good. There are 3 people, at least one of them should lose, not to get the good. Pigeonholing principle. That's very simple. So, without the loss of generality, let's say that player 1 loses. Excellent. Now, assume that the true setting now, because remember, I want to find a contrasample when this mechanism, no matter what it be, this M generic, but I think is going to fail by at least 2 delta. So, let the true setting be this one for this player and these 2 for the other player. Ready? 1, 2, and 3. Okay. That is the true setting. Now, let me choose the true value. The top for the first player, the bottom for the other ones in their set. Okay? That's good. Now, what are these guys going to do? Well, they play an undominated strategy. I don't know which one, but they could play SI, the blue SI, each one of them. And when they do, player 1 loses, because that's what I said. But then, you see, now we are done. Because who wins? One of the other 2. But no matter which of the other 2 may win, you can see that you have missed the social welfare by at least 2 delta. So the key to prove this is really to prove this damn intersection lemma. All right. If probabilistic things are good. So let's resume, hopefully, being together. The hard stuff is over. And in 5 minutes, I'm over too. So what have we seen so far? So we have seen that the second price mechanism is very resilient to alternative specification of preference and information structures. And that I think is a very good idea. We should design mechanisms which are much more resilient than the ones we have. And it is a classical mechanism. Why? Because like most things classical, has transcended the limits in which it was originally conceived. You take a good book, a classical book, is book for the generation for which it was written, as well for us. And the second price mechanism is really classical. And I hope to have told you that Knightian analysis of mechanism is viable. And actually, this second price mechanism not only is good, but is actually optimal. It was not designed for these players, but it's so good that no other mechanism can actually beat it in this setting. Can Knightian analysis go further? Say, okay, the second price mechanism, as you said, is a very elementary mechanism. Yes. Now we can do multi-unit auctions. For those in the know, it means now that I have M for sale, M identical goods. So, 2 Rolexes, 3 Fiat Cinquecentos, same brand, same color, same upholstery, same everything, okay? You have a value for one, you have maybe for the first copy, you have maybe a little less value for a second copy, but you still have of value to you. I have 2 cars rather than one, because the first one is in your shop, use the second one. If you get in a serious relationship, you don't want to get tangled who uses the car. So get the car, I take the second copy. So there is always a use for a second copy, even though there is marginal values. And there is a second price mechanism as a generalization that is called the Vickrey. And we've been able to characterize the undominated strategy for our uncertain player for the Vickrey. And they are naturally bounded too. So let me tell you what naturally bounded means in this case. Assume that my one player, I think there are 2 Cinquecentos, and I know that my valuation is 78 for the first Cinquecento and 60 for the second. Or 80 for the first and 50 for the second. So then the undominated strategy are simply this. So if you take the maximum of the first copy, which is 8, you put it here. The minimum, which you put it here, and the minimum, the maximum for these guys, the cross product is the undominated strategy. For instance, bidding 79.57 is legal and rational. So is building 78 and 55 or 8 and 51. By contrast, if you think about mix-max rationality, and if you do the analysis, the only thing a min-max rational player is to bid 78 and 52. Right? It's a bit too boxy. But this naturally bounded property again tells you that you cannot miss the maximum social welfare by much. How much? 2m delta. So if delta is small and the number of goods m is 10, even if it's 1,000, it's going to get, or 100, it's going to be pretty good. And frosting on the good, nobody can do better than the Vickrey mechanism. It's actually optimal too. You know what? Also the Vickrey mechanism is classical. Wow, that seems to be a walk in the park. You take a classical mechanism, you analyze in this type of uncertain player, and not only they perform very well, but they're actually optimal. Well, that had to stop somewhere. Let me tell you where it stops. It stops here, at unrestricted combinatorial auctions. So what is for sale are totally different, distinct objects, not all equal. An apple, an orange, an aircraft carrier is a salad of things which are totally unrelated, and my valuation for any subset of them is totally unrelated to each other, right? And not the sum of the various things. So for instance, I can value good 1 alone 10, good 2 alone 10, but the set of good 1 and good 2, not 20, but 50. Why? Because I interpret good 1 as the fork, good 2 as the knife, a fork as a value, a knife has a value, but if I'm together, it has much more value. Another player can say values the first good $1 million, and the two goods together 0. Why? Because he interprets the first good as the mansion, the second good as the mother-in-law, and you don't want them together. So, arbitrary. If they are arbitrary, the problem arises that this bounded property disappears. And with it, the good guaranteed performance. Because the best you can guarantee is the maximum social welfare minus 2 to the m times delta. Now, even delta is small. 2 to the m can be astronomically large. So, is the party over? Well, first of all, even if it were over, it wasn't so bad. At least we could analyze one mechanism and then a second mechanism. But let me tell you, with this last slide, you can actually do better performance, and actually, if you have RMUD players, and who are these guys? These are utility maximizers who resort to regret minimization only to refine their undominated strategy, if absolutely necessary. In other words, if I'm a rational player, traditionally people love, I don't know why, utility maximizer. Experimentally, we know that many players actually are regret minimizers. But somehow, in most of the mechanisms, we assume that they are utility maximizers. I start feeling that being a regret minimizer is like being a wimp, and the true rational player is a utility maximizer. I don't think so. But let me sell you this model, this type of player, and say, look, if I'm a rational because, yes, I'm a utility maximizer, and I choose an undominated strategy, very good, sir. If you have one, what do you do? That. By the way, if there is unique undominated strategy, then it's also regret minimizer, but we should not say because that's a bad word, okay? But assume now you have 2 free undominated strategy. Which one do you choose? You cannot use rationality alone to disambiguate your choice, but you must make a choice. At this point, won't you consider as a secondary order regret minimization among all the other options? I think it is reasonable. And if you do, then again, you have an absolutely excellent performance. Okay, I think it's enough for theorems, and now we'll do for hopes. So, hopes is that I hope that more Knightian analysis and actually design, today we only did analysis, also mechanism will arise. I really hope that more set theoretic modeling of uncertainty, at least in mechanism design, is desirable. My hope is to see a greater role for epistemic game theory, because I'm new to the field, but what I realize that the epistemic game theorists are very familiar with possibilistic beliefs, but somehow it's like they don't talk to their colleagues who do mechanism design, because somehow they design the mechanism in totally different ways. And I really hope, don't let Enzo dissuade you, that actually logic is going to have a great role in dealing with set theoretic analysis, because logic is actually, as Enzo said, very discrete. Finiteness is really the essence of it. So we are going to, I hope we're going to see a greater role on logic, at least in the analysis, if not, it's not on the thing. And finally, my really hope is that we are going to realize more resilient mechanism. Resilient to what? To all things that can happen. And one is that you don't know your valuation, but there are other things. People may collude. Complexity is another obstacle, and privacy is another obstacle. And I think we ought to have a mechanism which are really robust to all of them. And finally, my greatest hope is to have a really increased collaboration between economics, mathematics, philosophy, computer science, and anything in between. Because that is a very beautiful, big, and hard field, and if we don't join forces, we're not going to win. In any case, win or not, collaboration is fun. Thank you.
Thanks very much, Silvio. Are there questions or comments?
The intuition for the very first result, the simple one, on the second price auction with sets, is then very similar to the original result. So the original result is you have singletons, and therefore the singleton set of undominated strategies, actions, is the uniquely dominant action, right? But then the kind of intuition, the way you prove things is essentially the same, right?
No, actually,
or not. I mean, I'm just talking about. No, okay. So because I thought.
It's not the same. In fact, actually, but it's so simple that I can actually prove it to you in 2 minutes, and it's the best way to address the question rather than trying in English to do things. The difficulty is to realize that there's a possibility, because initially I thought it wouldn't be true. But once you realize, you have to realize, see, that's my insistence in at least 2 things in common. You have to play that. And let me show you how. Ooh, not there. Okay. Good. Okay. So here is what I want to prove, right? That is a lemma. It's not exactly my theorem, but it's very close. Which means that for every player I, for every candidate sets of my opponents, and for all candidate sets ki or ki prime on me, if they have 2 elements in common, then the probability that the mechanism allocates to me the good when I report the 2 candidate sets, because in dominant strategy the revelation principle applies, so you might as well consider only truthful mechanism. Or when is equal to that if I report ki prime. So that is the lemma. And the proof is actually very easy, because if 2 guys, k and k prime, have 2 elements in common, do you mind calling them x and y? Not at all. And without loss of generality, one of them is less than the other. Let's say that x is less than y. Okay. Then how do you prove that 2 things are equal? The good old-fashioned way. You prove that 1 is less than or equal to other, and then you separately prove that 1 is greater than or equal to the other, and therefore that to be equal. So let me give you the proof of that. The probability that I get allocated the good when I bid ki is less than or equal to when I bid ki prime. Assume that my true valuation set is really ki. Then, if the mechanism is indeed dominant strategy, then reporting ki should dominate reporting anything else, in particular ki prime. All right. And that, what does it mean? That is dominates means that no matter what my true valuation is in my set, my utility, which is the probability I get the good minus the price I pay in this case, or to be greater than the probability of the good minus the price I pay in the other case. All right, now we know this. Now we can do say, if my true valuation set were Ki prime, then reporting Ki prime should be dominating Ki, and therefore means that. Again, okay? Now let me look at these two things, and you say, well, look at, for all theta I, how about if I choose theta I equal x? Right? They both belong to theta I, so I can choose x. So let me do the substitution for you. That is the formula, right, that we get. So that now becomes true. Similarly, because Ki prime also contains x and y, it could be that, let's see what happens when, to this inequality, when actually theta I is y. Let me do the substitution for you. There. Okay. Thank you very much. This can go. Now what do? I have two inequalities. They're both true. One has x in it, one has y in it. Now what do? I add them up, member by member. And notice that these damn prices, they don't depend on x and y, they can go. These other ones can go too. And now what do? I look at these ones, this part is the same, so I can cross both out and express them by putting this on the other side. And I can do this similar to this. Okay, now notice that even though something happens with inequality, nothing does remain here. So I know that this guy, this product, is greater than or equal to this product. But what am I assuming? Without also general. That x is less than 1. So that means that this is positive. So I can get rid of it. Let's get rid of it. And that's what I want to prove. And then, done. Then I have to prove this, mercifully I will not, okay? And then that's QD. And then from this lemma, you prove theorem 1, QD. That's about it.
I mean, so this is very, this was very interesting, and I'm happy that I didn't express myself well, because I actually meant not theorem 1, but something much simpler, namely that the second price mechanism works. In the second price mechanism in undominated strategies works in the sense you said. And I was just saying, I was just commenting that at least according to my understanding, the intuition is
that's the classical one, yes. So yes, once you remove anything below your smallest value and anything above the smallest value, no matter what you bid into here, right, you want to choose, this is really the worst case. I chose it and say, well, it can be another case. No, all other cases are no worse than that.
And the other thing is, basically, it doesn't matter whether, so basically all that matters here is the minimum, the smallest and the largest member of the sets, right? Yes. So you might as well have intervals and it doesn't make any difference, right?
Yes, yes, yes. But I believe that for the motivation that we skipped, it is good to talk about also discrete sets. For the proof, interval will be okay. Because if you take, so if I were to sell this to a very severe economist, I would say, well, take the Knightian model. And the Knightian model says that a player knows a set of distributions from one of which his type is drawn. And then people would agree that just because it's a classical thing, it was defined 100 years ago. So, and Knight has generated among his students 3 Nobel Prizes in economics. They don't contradict it very much. He has enough clout. So I want to ride on his coattails. Say, well, he said it. Okay, so given Aristotle was mentioned yesterday, so we could use Knight instead. Then I'm going to say, but I am risk neutral. So I take a set of distribution, now I take the expectation, I have a set of numbers. Now where do this set comes from? I really believe that what I'm finding when trying to explain the result is that most people buy the expert model. Because if you have, you hire 3 experts and they give you 3 different distribution, what are you going to do? So now you can take the expectation, now you have 3 numbers. And so it's very hard to have, infinitely many experts, but the result holds also if you have infinitely many, even though not interval necessarily, but even uncountable set. So I did not want, you're right, I could define right away, and I was, in one attempt, I tried to define it like this, but I felt there was some pushback. And the pushback was, how can it be that you know that your thing is, your evaluation is between A and B? Why cannot B? How can you discard A minus epsilon? Right? I'm sorry, when I can. So if I go the other way, so I have a set of distribution, when I take the expectation, whatever happens to be, and if they come from experts, that's okay. So part of the motivation is hard to say that even though I could do, nothing changes in the theorems if I start with intervals, is a little bit easier, I found, and certainly not losing any generality, but actually add the possible motivation of expert motivation. Nobody has infinitely many experts, let alone uncountable. So that's why I stated in that way. But you're right, the whole thing could be done with intervals.
Then more questions? Can I ask you to go back to the last slide of your personal hopes? I'm sorry this is going to take some work, but...
Oh, no.
Last one, yeah?
Yep.
No, the last one, just the very...
Oh, the last one?
Yeah.
Oh, all right. So, okay. So, look, I have a convenient thing. I click here, okay? So what do I mean resilient to collusion, complexity, and privacy? Okay. I love mechanism design. But remember, I was a cryptographer. And once a cryptographer, you remain a cryptographer. A cryptographer has an outlook on life which is very, I should say, realistic. Another body says it's very pessimistic. I think realistic is the right word. So if I look at mechanism design with my cryptographic lens, I see collusion, complexity, and privacy to be real problems. So let me illustrate collusion. The traditional notion of solution concept is really an equilibrium, right? Here we have the players on a plank, nobody wants to move. If you move, you precipitate down in the abyss. Okay. And here there are, however, a pack of money over there. And there is a pool and there is a rope. Okay? So if this player wants to get the money, she can't because pools, nothing happens. But it is where chimpanzees, never mind humans, and you replace the money with bananas. It won't take long to 2 chimpanzees to figure out that they can actually do this to the perdition of ours. Because now collusion allows you to deviate with profit from the equilibrium. So to me, an equilibrium is not enough without analyzing collusion. In other words, collusion is a problem, and let me illustrate this with the tax audits. Here is the IRS, and here are the players. And the IRS, spends a lot of money to collect, to investigate tax declarations, because otherwise you declare that you earn at 0 and you paid 0 taxes. But I suggested to the IRS, there's a brilliant idea. And you say, say this. If you declare that you, player I, declare that another player J has paid correctly his taxes, I promise not to audit player J. And that is dominant strategy for you never to write this declaration if it's not true. Why? Because if J has cheated on his taxes, and these taxes were not properly collected, an epsilon fraction of these taxes you would benefited from in infrastructure, hospital, roads, all this other good stuff. Right? So, nonetheless, if the IRS use this, which is dominant strategy, to say, what happens? Say, look, the IRS is going insane. If they understood this, they say, I say that you pay your taxes, you say that I pay your taxes. And the only money that is going to be made is the post office makes money due to the flood of declarations like this that do the crime. So really dominant strategy, here is an example of dominant strategy that with collusion really is totally meaningless. So individual incentives and collusion don't disappear. Complexity is important. Because if things take too long, here is the designer, here are the players, the game is still going on, they all died in between. So that is not a good solution. So he says, okay, just because you insist the perfect solution, how about if you approximate it? Well, but if you approximate it, it's no longer truthful. Right? Because things are truthful if you are really on the nose, and if you say 99% is no longer truthful. So 90% of the truth is different from 9% of baloney. So in other words, incentives goes against approximation. And finally, privacy. I mean, so mechanism design that is privacy is really neglected. But somehow you can give people incentives, but people have the desire for privacy prevents them from being truthful. We were talking Pierpaolo yesterday and Massimo too to say think about in an auction, what is the best the auction will be? That in dominant strategy you reveal how much you value the objects. If it is a new oil well or a new technology or whatever. But imagine that you declare truthfully and you don't win the auction. And then you declare what your preference is for the object to all your competitors. Are you really saying that you have zero utility? I believe you have a negative utility. So I think that people care about privacy, period. And if game theory wants to be a theory of human interaction, it better take care of privacy. Because divulging your private information, what does it mean that you value privacy? It means that if you reveal it, you have a negative utility by definition. Because as an economist, we quantify as money anything. So truthfulness and privacy don't go together. So if you take care of a mechanism, and now it's pulled by rationality, by collusion, by privacy, by others, where is it going to go? World Wide Web? No, that is who will win? Very unclear. So I really believe that if you really want to have a mechanism in the real world, you really have a whole solution to collusion, privacy, and things. That's why I really believe it ought to be a collaboration of various fields, because the opportunity is enormous, but the way there is very hard, very arduous. And it's going to keep us occupied for a century.
And I think on this note, I'd like to thank our speaker again and everyone else, because we're done. Thanks very much.